Hello and good morning everyone. I welcome you all to India's largest e-learning platform Unacademy, and I welcome you all to Gate Conqueror channel. We are into antennas MCQ series. The very important antennas MCQ series. This session will be part 4. And this antennas MCQ series will be useful for your GATE, engineering services and other competitive exams like BARC, HL and wherever antenna syllabus is there. For all those exams, this particular series will be useful. Yeah. Good morning everyone. Just confirm the video and audio once, dear. Yeah, it looks good, it looks good, it looks good. It looks good, dear. Yeah. So we are into antennas MCQ series. Before we start the class, let me introduce myself. I am GC Reddy. Having overall 15 years of experience in teaching, guiding and mentoring GATE and ESE aspirants, and 12 plus years of experience in teaching only GATE. And I worked as motivational speaker pan India from the past 12 years. Expert in field theory and communications. And this is the official Telegram channel for the GATE Conqueror. For the GATE Conqueror team, you can join here to access all the faculties of the GATE Conqueror team, including the legendary K.N. Rao sir. And the good news for all GATE Conqueror channel followers is we had increased in number now, and we are ready to go for comprehensive courses for GATE 2023. Bhaskar, how are you? That was a wonderful series that is going on, Bhaskar. This will be very much helpful for you. You can inform all your friends also. There's a very good series going on. So the good thing for the GATE Conqueror followers following us from the past 2 years is like, as we had increased in number, now we are ready to take up full comprehensive courses on EC and electrical and complete the syllabi in hand. Okay. As a part of that, I will be completing EMFT and communications. EMF for electrical, EMFT for EC and communications for EC. I will be taking the responsibility to complete. And before we move in also, I'll try to explain how much data is available on our channel for EMFT, because I'm talking about only comprehensive courses. Of course, so much of data is there for EC and electrical, and so much of EMF other stuff is also there. But the videos that are useful for preparation for GATE 2023, I'll explain how many videos are available and how much data is available before we start the MCQ series part 4. How are you, dear Bhaskar? So we are into antennas MCQ series. We are into antennas MCQ series, where we are supposed to cover 500 MCQs on antennas, useful for all the competitive exams, including GATE and ESE. So that is what we are trying to plan. And those who are trying to learn from the Gate Conqueror channel, the content available on Gate Conqueror channel for EMFT I'll explain very shortly. Then we'll start the MCQ series. If you want to prepare for EMFT through Gate Conqueror channel, there is one playlist targeting Module 1. Module 1 of EMFT for EC people is Elements of EMF Theory. In this Elements of EMF Theory, this is complete syllabus. This is complete syllabus for electrical students, and of course module 1 for EC, one of the module for EC, or around 20 to 25% of the syllabus for EC. And this will be useful for both Gate and engineering services. We had created a playlist on this module 1, which contains 40 videos spanning duration of 50 hours. These 40 videos and 50 hours of 50 hours duration will be useful for Gate and ESC preparation for both EC and electrical. For electrical, it is complete syllabus. So my intention was to cover EC also. So along with Gate, I want to cover ESC. That's the reason in this module 1, we explained complete theory, all derivations. All derivations. You can't see that many number of derivations anywhere. Almost everything I derived. And we have done numerous number of practice questions. You can't see that many number of self-designed questions also in any playlist. Covered all the previous year questions. What else you want here? Previous year questions we got lot of practice questions, complete theory, and all derivations, such that it will be useful for both Gate and ESC and as well as for other competitive exams. So this playlist you try to check out. 40 videos, 50 hours playlist is there. Just try to check out. Check out on this particular playlist, which will cover module 1. In module 1, we covered electrostatics, and magnetostatics as a part of static field theory. As a part of static field theory, we covered electrostatics and magnetostatics. In electrostatics and magnetostatics, the main topic that we had covered are Maxwell equations. Of course, so many number of topics are there, but if I need to give synopsis of what we had covered, then I can say we had covered Maxwell equations for static fields. What we had covered under Maxwell equations are equation 1, closed surface integral of d dot ds is equal to volume integral of rho v dv, integral form of Maxwell first equation. Del dot d is equal to rho v, differential form of Maxwell first equation. Source Gauss law for electrostatics. Second equation, closed loop integral of E dot dl is equal to 0 plus del cross E is equal to 0. This was a property called conservative property of electric field. These two are from electrostatics. These two are from electrostatics. Then we covered Ampere's law. Closed loop integral of H dot dl is equal to surface integral of J dot ds, integral form del cross H is equal to J, differential form. Source Ampere's law. Fourth one, closed surface integral of B dot ds is equal to 0. Integral form, differential form del dot B is equal to 0. Source Gauss law for magnetic fields, also called as non-existence of magnetic monopole, also called as non-existence of magnetic monopole. These are the main things that we have derived, which are Maxwell equations for static fields in static field theory. Besides this topic, we also covered the very important topics like, only I am trying to highlight the very important topic. Please go through the playlist for detailed discussion and solutions, theory and problems on this particular playlist. This playlist is very, very important here because it comprehensively covers everything related to elements of EMF theory like never before. Besides Maxwell equations for static fields, we had covered Poisson's and Laplace equations, we had covered Poisson's and Laplace equations and their applications. Some wonderful derivations have been done on this, and so many applications, and also numericals related to all the different coordinate systems like Cartesian, cylindrical and spherical are covered with respect to the applications of Poisson's and Laplace equations. Besides this, we had covered the very important boundary conditions, and also we had derived the values of different types of capacitors and inductors and their applications, and numerous number of numericals on capacitors and inductors. Capacitors and inductors. This also we covered. This also comprehensively we covered. Clear? So this is what we had covered in static field theory and in time varying field theory. In time varying field theory, we derived Maxwell equations for time varying fields. Maxwell equations for time varying fields. If you go for Maxwell equations for time varying fields, equation 1 and equation 4 of static fields will be same. Maxwell equations for static fields and Maxwell equations for time varying fields, equation 1 and 4 will be same. 2 and 3 are modified. Equation 2 is modified. By Faraday's law. Equation 3 is modified by Maxwell contribution. So, in time varying field theory, we derived Maxwell equations for time varying fields, in which we have derived Faraday's law, and we have seen applications of it, and numerous problems on Faraday's law has been done. Maxwell contribution. Also called as inconsistency of Ampere's law. This we had covered in module 1. So I can say here, no other YouTube platform will provide such a detailed discussion on elements of EMF theory. Complete syllabus for electrical, module 1 for EC. 40 videos are there. Most importantly, 50 hours of recording is available. Mostly, dear, I can say mostly what you get is 10 to 12 hours, not more than that. 1 second, dear. Give me 1 second. Give me 1 second. So, just 1 second here. 1 second. This detailed discussion on elements of EMF theory will rarely find. Sorry. Thank you. Okay. So, on Gate Conqueror channel, one of the most important playlists that you need to go through is this playlist, which covers complete syllabus for electrical. You can prepare for GATE and ESC comfortably. And it is most updated with all the previous year questions, including the latest ones. GATE 2022 solutions I'll add. And also ESC solutions I'll add soon. This both I'll add at a time. GATE 2022 and ESC 2022 solutions I will add into this particular playlist very soon. Other than that, it is fully completed. It is fully completed. So that you can access. That you can access. This thing you can access. Okay, this thing you can access. Yes, Rajesh, how are you? I was just thinking, how was your preparation going on? How are you doing? So this you can access dear module 1. And you can access module 2. Module 2 is EM wave propagation. You can access EM wave propagation, module 2. For this, a playlist is created. With 8 videos. And 18 hours of recording is done. What we have in EM wave propagation is EM wave propagation in free space. Free space means sigma is 0. Epsilon r is 1 and mu r is 1. We have discussed about how EM wave propagates, what is the nature of EM wave, how it propagates in free space, and once it propagates through free space, what is the value of alpha, beta, its velocity and intrinsic impedance. For the derivations and detailed explanation, please go through this playlist. One more wonderful playlist. Then we discussed about EM wave propagation in materials with finite conductivity, means sigma not equal to 0, epsilon r greater than 1 and mu r greater than 1. Here too we have derived alpha, beta, velocity, eta, and loss tangent or dissipation factor. Which is useful in bifurcating the materials into good conductors and good dielectrics. And also, we have derived the general expression for and also we have derived the general expression for alpha and beta. Then we discussed on EM wave propagation. We discussed on EM wave propagation. In good conductors, good conductor implies sigma far greater than omega epsilon. Then we derived the terms like alpha, beta, velocity, penetration depth, delta, so called as skin depth, also called as skin depth under special conditions. Derived relaxation time, closely related to penetration depth concept. Derived surface resistance, which you got as 1 by sigma delta. And also we have derived intrinsic impedance. Again, detailed explanation of this, the derivations for this. You can go through this particular playlist. And also we discussed about EM wave propagation. In good dielectrics, sigma far less than omega epsilon. Here too we have discussed, derived the values of alpha, beta, velocity and eta. Fifth, we had seen EM wave propagation in perfect dielectrics. Perfect dielectric means sigma is 0, epsilon r greater than 1 and mu r is greater than 1. Sixth, completed pointing theorem. Theory is completed, and what is pending and trying to write it in red. Numericals on pointing theorem are pending. Previous year questions and practice questions are pending. 7. Wave polarization is pending. Theory, derivations and numericals are pending. 8th one, reflection and refraction of plane waves. Deflection and refraction of plane waves. Theory, numericals are pending. In this reflection and refraction of plane waves, we derive terms like Brevis triangle, total internal reflection and critical angle. Whatever I had written in red here especially are pending. So I can say around 85% of the syllabus is completed in module 2. And in this week, March first week, I will complete this remaining part. Maybe it will take around 7 hours more. So overall, we'll have some 25 hours playlist for EM wave propagation. Already we have 50 hours of playlist for module 1 recorded and 18 hours already here. 7 more hours I will add. It will be done to 75 hours in 2 modules. We'll have 75 hours in 2 modules. It will be 75 hours in 2 modules. Module 3, transmission lines, not completed, will start in 2nd week. Module 4, waveguides not completed, will start along with transmission lines. Okay. This we plan to take around 40 hours. 40 hours on this. And probably around 35 hours for waveguides. And module 5, is antennas and optical fiber communication. Optical fiber communication I'll take up. This I'll take up in March 2nd week. And after this series is done, we'll go for optical fiber communication. 15 hours to 20 hours. Okay, make it 20 hours. 20 hours we'll take on optical fiber communication. And the good news is antennas is done. We're covered antennas using antennas. Mahamarathon series, in which a playlist is created. With 18 videos and 38 hours. And soon we'll add some more videos here. Adding practice questions, minimum of 12 hours. I'll add. This is already available. This I'll add. I'll make it 50 hours. So module 5 is ready. And again, on antennas, you take any online platform. On antennas, you take any online platform. Max 6 to 8 hours of content will be available on antennas. Against that, we got 38 hours already, and I'm ready to teach 12 more hours. So already the number of hours that are available on Gate Conqueror channel: 50 hours of module 1, 18 of module 2, 50 of module 1, 18 of module 2, and 38 of module 3 already available. And this I am only talking about Gate and Engineering Services preparation. Other content, so much content is there. So this will be around 106 hours of content is already available. Here I'll add 7 hours. Here I'll add 12 hours. Immediately, the next target is to add this 19 hours to the content. Then 40 hours planning for module 3, 35 for module 4, make it 20 for OFC. So around 95 hours more we need to plan. This both put together 114 hours. I'll add to EMFT. Already 106 available. You need to understand here, max to max, I'm telling you, 40 hours they'll finish EMFT. Complete EMFT. I already recorded 106 hours. And I'm ready to record 114 more hours. So this EMFT will be 220 hours recording. You cannot, I'm telling you, you cannot find more detailed explanation than this. It is almost like 5-fold more than what others will offer. Exclusively available on Gate Conqueror channel. So ask all of your friends also to subscribe here. In this way, in each subject, very much in detailed explanation will give on each subject, and I am planning around 220 to 250 hours of full comprehensive series on communication system. After EMFT, I'll start communications. 220 to 250 hours of detailed series I'll plan there. I'll give more details in some other session because this is related to EMFT I discussed here. In antennas also here, we had covered complete antennas and wave propagation. Is that clear? Antennas also, as I told you, generally 8 hours of content will be available for antennas. Against that we got 38 hours. Why? Because I recorded antennas, or I took classes for antennas which are helpful for both gate and ESC. I just took it in such a way that it will be useful for both gate and ESC. In antennas, we had covered basic terminology of antennas, current distribution in antennas, radiation mechanism of antennas, how VI waves are converted to EM waves and EM waves are converted back to VI waves by antennas, which will be discussed under radiation mechanism of antennas. Very rare content here. Radiation mechanism is very rare content that you can find on YouTube. That we have discussed radiation mechanism of antennas, in which we have discussed about single wire, two wire, and dipole antenna radiation. Then we have discussed about radiation pattern of antenna, in which we have discussed about main lobe, side lobe, back lobe, nulls, first nulls, beam area, FNBW and HPBW and many more. All this in radiation pattern of antenna we have discussed. Then we discussed about radiation parameters of antenna. Under radiation parameters of antenna, we discussed about simple gain, power gain, directive gain, directivity, efficiency, radiation intensity, radiation resistance, antenna temperature, beam area, and many. All these we have discussed under radiation parameters of antenna. Why 38 hours I am trying to explain. Why we took so many hours. What we had covered in these 38 hours I am trying to explain. And we had covered antenna arrays. In antenna arrays we covered 2-element arrays. Under 2-element arrays, we have done all the case study for all the 5 cases. Case 1, D is lambda by 2. Alpha is 0. Resulting in broadside array. Case 2, D is lambda by 2. Alpha is pi. Resulting in Indified array. D is lambda by 4. Alpha is pi by 2, resulting in heart-shaped pattern. D is lambda by 4, alpha is minus pi by 2, the reverse of heart-shaped pattern. In case 5, D is lambda, alpha is 0, resulting in flower-shaped pattern. All these 5 cases in detail we are discussed. About all these 5 cases we are discussed in detail. That was about 2-element arrays. For detailed explanation, please refer the Antennas Mahamarathon series. Then we discussed on one second. Yeah, 2-element we have discussed. Then we have discussed on n element arrays, in which we have discussed on broadside array and Indified array. Besides this, we have discussed on the special arrays, called as Hansen and Woodyard array for increased directivity, also called as Indified array with increased directivity. For detailed explanation here, please go through Antennas Mahamarathon series, and we discussed on binomial arrays, which will eliminate side lobes, useful in radar applications. We discussed about its advantages and disadvantages very clearly in Antennas Mahamarathon series. After that is, we went for 7 sisters. Under 7 sisters, we had covered folded dipole antenna, Yagi-Uda antenna, helical antenna, microstrip array antenna, horn antenna, parabolic reflector antenna, and lens antennas. It's also wonderful combination. 7 antennas put together were discussed, which I termed as 7 sisters. 7 sister antennas, which are very, very important. About this we have discussed, and besides this we had also discussed about resonant and non-resonant antennas. Under resonant we have discussed about monopole and dipole. Under non-resonant we have discussed about V antenna, inverted V antenna, and rhombic antennas. Besides which, it also covered antenna measurements. Under antenna measurements, we had seen the basic setup required for radiation pattern measurement, and we discussed about the methods of measuring gain, we have discussed about the methods of measurement of directivity. Under gain we have discussed about 3 antenna method, or also called as first method. Then we have seen measurement of absolute gain, by using two identical antennas, two identical standard antennas. Which is called second method. And in directivity, the double integral will be involved. When for graphical numerical methods, the graphical numerical methods that we have discussed, or orange slice method, and conical cut method, These are the topics we had covered under antennas, and this series on antennas includes antennas plus wave propagation. This week, Amit, when you start, rest of the theory is left for wave propagation. This week, maybe from March 2nd, day after tomorrow I'll start. MCQ series will go on, along with that I'll start, okay? Balan is good. Okay, Balan is a good book for antennas. And here we have covered antennas and wave propagation. One second. Yeah, in this module 5, we have covered antennas and wave propagation. In wave propagation, the second part of the antennas and wave propagation, the second part is wave propagation. In wave propagation, we had covered principal modes of propagation, the principal modes of propagation, one second. Covered the principal modes of propagation. The principal modes of propagation are ground wave propagation, which is up to 2 megahertz, which will allow frequencies, namely very low frequency, 3 kilohertz to 30 kilohertz, low frequency, 30 kilohertz to 300 kilohertz, and medium frequency, 1 second here. Yeah. And medium frequency from 300 kilohertz to 3 megahertz, almost all the medium frequencies are covered here. Because ground wave propagation supports up to 2 megahertz, and beyond 2 megahertz the losses will become very high. Why the losses will become very high and all? You try to go through Antennas Maha Marathon series. In that detailed explanation will be given why only these waves are allowed. Very low frequencies, the wavelength are very long waves. Its wavelength is very long, therefore they are also called as very long waves. Low frequency waves are called long waves. Medium frequency waves are called medium waves. Basically, in principal modes of propagation, we allow very long waves and medium waves. And of course, as I told you, as the frequency increases, losses increases. Losses are due to different reasons like wave tilting and absorption of Earth's surface. Absorption of Earth's surface. How this wave tilting and absorption will affect the attenuation of ground waves. For the details, you can please go through the Antennas Maha Marathon series. The range of ground wave propagation is given by 100 by cube root of frequency, given in kilometers. When I consider the maximum frequency that is allowed, 2 megahertz, for the maximum frequency value, the range you get is 80 kilometers. And below 500 kilohertz, generally applications are very low. So practically possible frequency that can be operated is 500 kilohertz. For this, the range is around 126 kilometer. Therefore, the range of ground wave propagation 80 to 126. Practical possible. Theoretically, you can decrease this frequency. The number will increase up to 200. Practical importance is very less. Ground wave propagation, the major application is AM radio. So that's about ground wave propagation. More detailed analysis of ground wave propagation you can see in Antennas Maha Marathon series. Any doubts here? You can please ask. Any doubts you can ask. Then wave propagation, principal modes of propagation. Second one is sky wave propagation. Second one is sky wave propagation. The second one is sky wave propagation. Sky wave propagation is between 2 megahertz to 30 megahertz. Basically, the capacity of the sky wave propagation to allow waves depends on the capacity of the ionosphere to reflect such waves. as it uses ionosphere. Skywave propagation is also called as ionospheric propagation. Is also called as ionospheric propagation. Clear? And here ionosphere is a region which is between 50 to 400 kilometers above the Earth's surface. Ionosphere is a region 50 to 400 kilometers above the Earth's surface. We will continuously reflect and come back. The major layers, the major regions of the ionosphere are D region, E region and F region. These are the major layers. So much of discussion is there on these ionospheric layers also. For detailed explanation, I recommend you to go through the Antennas Mahamarathon series. And this region is called ionosphere because it has ions. Ions are formed when molecules are subjected to sunlight. Sunlight acting as ionizing agent. It releases alpha, beta, gamma, X-rays and other kind of rays which are used as ionizing agents. And when these molecules which are dwelling at different heights, different molecules will dwell at different heights. When they are subjected to these ionizing agents, some of these molecules will release an electron to become a positive ion, the others will accept to become a negative ion, and thereby, because of the formation of ion, the layer is called, or the region is called ionosphere. Of course, lot of theory is there, recombination of ions and all the concept is there, that you can go through in the Antennas Mahamarathon series. So, especially, skywave propagation is utilized to transmit high frequency waves, mainly frequencies between 3 MHz to 30 MHz, and these frequencies has short wavelengths. Therefore, this propagation is also called as short wave propagation. It's extremely useful propagation, very long distance communication. Round the globe communication is possible using skywave propagation, and a single hop skywave can cover a distance not greater than 4,000 kilometers. By using multi-hop communication or multi-hop propagation, round the globe communication is possible. Clear? Any doubt, let me know, dear. Any doubt, please let me know. Yes. So that is ionospheric propagation. The second one. Third one. Space wave propagation. Third one, space wave propagation. is between 30 megahertz to 300 megahertz. Allows very high frequencies as it uses line of sight. It is also called as line of sight propagation. In a line of sight propagation, the transmitting antenna and the receiving antenna must see each other for the communication to be possible. This is called line of sight propagation. In line of sight propagation, we will have direct waves and indirect waves. Direct waves are those which are directly reaching from transmitting antenna to receiving antenna. And indirect waves are those which are reaching the receiver after reflection from the earth's surface. This is direct wave and this is indirect wave. And resultant wave is always the sum of direct wave and indirect wave. In general, direct wave and indirect wave are out of phase by 180 degrees. So the resultant wave depends on the phase shift between the direct wave and indirect wave. As these two waves are traveling different paths, therefore they have path difference and thereby they have phase difference. Now for the line of sight to be possible, the transmitting antenna and the receiving antenna must be able to see each other. This height of the transmitter, this height of the receiver. And the range of space wave propagation we have derived in the antennas Mahamarathon series. You can please refer that video where we have defined. You can define range of space wave propagation as 3.57 into under root HD plus under root HR kilometers. The range is given in kilometers. HD and HR, height of transmitter and height of receiver, are measured in meters. And this can be approximated also to 4 times of under root HD plus under root HR kilometers. This can be approximated to 4 times of this. And practically possible, height of transmitter and height of receiver are 100 meter. For these values, if we calculate the range is 3.57 under root of 100 plus under root of 100, 71.4 kilometers. If you take 4 times of this, then it is 80 kilometers. So that's the range of space wave propagation. So these are the 3 principal modes of propagation on which we can rely. Besides these 3 principal modes of propagation, we also discussed about the special modes of propagation. The special modes of propagation are scatter propagation, which is further classified into tropospheric scatter propagation, or also called as forward scatter propagation. And other is ionospheric scatter propagation. In tropospheric scatter propagation, This tropospheric scatter propagation is formed due to the formulation of turbulence region in the tropospheric region, and turbulence region is formed because of the movement of masses or eddies or air blobs of different electric constant moving in random directions. Because of this, tropospheric scatter propagation or forward scatter propagation takes place. It happens between frequencies between 100 MHz and 10 GHz. That means it is operated in a small part of VHF, UHF, and a small part of SHF. Tropospheric scatter propagation. By using tropospheric scatter propagation, we can transmit signals beyond horizon, the range of 160 kilometers to 1600 kilometers. As the formation of the turbulence region is not stable, these kind of modes are treated to be special modes of propagation. Unlike principal modes of propagation, we cannot rely on this. Second is under scatter propagation. First one, tropospheric scatter. The second one, ionospheric scatter propagation. Ionospheric scatter propagation is mainly due to the formation of sporadic E layer. Sporadic E layer is a layer that is highly dense layer that is very closely formed to the E layer. Formed suddenly due to the infiltration of the top layers, geomagnetic disturbances, and ionospheric storms. This sporadic E layer is responsible for M-type propagation. Again, more in detailed explanation of this M-type propagation, you please go through Antennas Mahamarathon series. Using ionospheric scatter propagation, we can transmit the signal in the range of 1000 kilometers to 2000 kilometers. The frequencies are operated much beyond the general frequency range of 2 MHz to 30 MHz. They are operated frequencies in the range of 25 MHz to 60 MHz. Clear? Besides scatter propagation, one more special mode of propagation is ductive propagation. Ductive propagation is mainly due to formation of inversion layers in the coastal region or above the oceans, where water vapor content and humidity is very high. Under these conditions, inversion layers are formed. In general, standard tropospheric region, with increase of height of every 1 kilometer, temperature falls at the rate of 6.5 degrees Celsius. But in the formation of inversion layers, temperature increases with the increase of height. This is said to be the formation of inversion layers. When these inversion layers are formed, the refractive index value will change drastically. The refractive index value will change drastically, and the general refractive index n cannot be used. Small m cannot be used. In the place of that, we use a modified refractive index or a new refractive index, which is 0.0003% greater than unity. As this is very close to 1, we generally use an excessively modified refractive index m, which is given as n minus 1 into 10 power 6. And basing on the variation of m with respect to h, that is height, we form M curves. If dm by dh, the slope of m with respect to dh is positive, you treat as standard atmosphere. Dm by dh is negative, then we say the formation of inversion layer. Based on the type of duct that is formed, ducts can be of two types. Ground based duct and elevated duct. Again, in detail explanation about M curves and different kinds of ducts that are formed. You can see them in detail in the Antennas Mahamarathon series. And whatever duct is formed, it may be ground based duct or elevated duct. The maximum width is 1000 feet. 305 meter. 1000 feet or 305 meter. Is that clear? That's the maximum width of the duct. And always remember to place the antenna within the duct so that most of the waves are trapped by the duct. And duct acts as a leaky waveguide. Therefore, the cutoff frequency for the leaky waveguide is determined by the formula lambda max is equal to 0.084 d power 3 by 2. This lambda max is utilized in the calculation of FC. F is C by lambda, FC is C by lambda max. Which determines the cutoff frequency of the duct. So lower is the width of the duct, higher frequency is required to allow through the duct. Higher is the width, lower frequencies can be allowed. That's the bottom line. So these are the special modes of propagation. Besides this, we had also seen structure of atmosphere, in which in detail I explained structure of troposphere, and structure of ionosphere. Then also we derived the most important derivation for refractive index of ionosphere, which you got it as mu or n is equal to sin I by sin r under root of 1 minus 81 n by f square. Then we are seeing the concept called mechanism of radio waves bending by ionosphere. Also beautiful concept which explains you the mechanism of radio waves bending by the ionosphere. Then we have derived the terms like critical frequency, given by Fc. Then we define virtual height, then we define maximum usable frequency, and also we define least usable frequency, skip distance, this maximum usable frequency FMEF, this is virtual height H prime, which is CT by 2. This critical frequency FC is 9 root nm. FC is in megahertz. Nm will be in per meter cube. And ready for maximum usable frequency is defined as FC into secant I. It is always greater than FC by value of secant I, which is called as secant law. Flat depth FMEF is equal to FC into under root of 1 plus d by 2h whole square. This is for flat depth. And skip distance, d skip is equal to 2h into under root of FMEO by FC whole square minus 1. And also we have seen optimum working frequency, which is 85% of maximum usable frequency. These kind of parameters we have defined, and we define a derived range of space wave propagation. We derived the derivation for received electric field strength in space waves. And also we had observed the effect of curvature of Earth. Effect of curvature of Earth on space waves. So we are seeing ionospheric abnormalities, which included sudden ionospheric disturbance, sudden ionospheric disturbance is also called as Mongol-Dillinger effect. Ionospheric storms, along with that we have seen ionospheric storms, sudden ionospheric disturbances, ionospheric storms, and sunspot cycles. Besides this, there are total of 10 ionospheric abnormalities, of which these are the main. Again, if you want in detailed explanation of this, please refer the Antennas Mahamarathon series. And besides this topic, we also discussed about fading and path loss calculation. What is left out is some previous year questions and 100 to 200 more practice questions will do. And Antennas Mahamarathon series, which will fully cover module 5. So around 106 hours of recording is already available on EMFT. And I am planning to record 114 more. So total 220 hours of recording will be there. Is that clear? Now, let me answer this question, dear. Everyone try to answer this question. Everyone try to answer this question. An array is said to be linear if all the elements of the array are, I repeat it, an array is said to be linear if all the elements of the array are fed with equal phase of current, fed with equal amplitude of current, equally spaced, all the above. An array is said to be linear when the elements of the radiators of the array are equally spaced. Question number 1, option C is the answer. Second question. A uniform array is one where the current is. A uniform array is one where the current is. An array is said to be uniform when the current of equal amplitude is fed. Uniform array is one where the current is equal or the current is equally fed. Question number 2, option A is the answer. In a broadside array, radiation is dash the axis of the array. This is the axis of the array. Axis of the array. Array axis will be different. Individual radiator axis will be different. For example, you are considering an array of 4 radiators. If you are considering an array of 4 radiators, this is the axis of the individual radiator, whereas this is the axis of the array. Now you listen carefully. In a broadside array, radiation is dash the axis of the array. In a broadside array, the radiation is perpendicular to the axis of the array. Remember dear, don't get confused between axis of the array and individual antenna array, individual antenna axis. Don't get confused between axis of the array and individual antenna axis. So a broadside array is one where the radiation is perpendicular to the axis of the array. Axis of the array is nothing but axis of all these arrays. So in a broadside array, the radiation is dashed to the axis of the array, is perpendicular to the axis of the array. Question number 3, option B is the answer. Geometrical structure of broadside array. Geometrical structure of broadside array is similar to which kind of array? Geometrical structure of broadside array. This is a broadside array. These are the feeder lines. The geometrical structure of broadside array is similar to dash. This is my broadside array. I can build a similar structure and I can say this is Indified array also. That means broadside array and Indified array have same design. The geometrical structure of broadside array is equal to Indified array. They only differ in the way the current is fed. In a broadside array means this is the array axis. Radiation is perpendicular to the axis. The radiation is perpendicular to the axis. In a broadside array means the array which will radiate perpendicular to the axis. In broadside array, the maximum radiation occurs at this theta 0, theta 90, theta 270, theta 360. In a broadside array, maximum radiation occurs at 90 and 270. 0, 90, 180. 0, 90, 180 and 270 degrees. In a broadside array, maximum radiation occurs at theta is 90, theta is 270. 90 and 270. In a broadside array, minimum radiation occurs at, if you consider this as a broadside array, here the minimum radiation is along 0 and 180 nulls. Minimum radiation is along 0 and 180. The answer is null. In broadside array, half power point occurs at, in a broadside array, radiation is perpendicular to the axis. The half power points are occurred at, this is half power point, this is a half power point. The half power points are occurred at plus or minus 60 or plus or minus 120. Radiation pattern of broadside array is, a broadside array always radiates perpendicular to the axis and is always, the radiation is bidirectional. It is bidirectional. Therefore, the radiation pattern of broadside array is bidirectional. Option 8, question number 8, option B is the answer. Broadside array radiation pattern can be converted into unidirectional. Broadside array radiation pattern can be converted into uniform. Broadside array radiation pattern can be converted into unidirectional by placing an array at the dash distance beside the original array. If this is a broadside array which will radiate bidirectionally, behind this if you place one more broadside array, behind this, then broadside array generally gives you bidirectional radiation pattern. But when you try to keep one more array at a distance of lambda by 4, then this broadside array radiation will become unidirectional. That will become unidirectional. To do that, we need to place an array behind the original array, a distance of lambda by 4. Broadside array pattern can be converted into unidirectional. Just now I told you how broadside array can be converted into unidirectional by using a couplet. Couplet is nothing but placing an array at a distance of lambda by 4 behind the original array. The array is said to be, the array that is behind the original array is fed with a current led in phase by 90 degrees. Indified array radiation is dash the axis of the array. Always indified array radiation is along the axis of the array. Current feeding structure of broadside array is similar to what? Geometrically, broadside array and Indified array are similar. But current feeding structure of broadside array is similar to what? It's similar to collinear array. Next, in Indified array, radiation pattern. In Indified array, maximum radiation occurs at theta 0, theta 90, theta 180, theta 270 and theta 0. In Indified array, maximum radiation occurs at 0 and 180. In Indified array, the minimum radiation occurs at this Indified array. The minimum radiation is occurring at these points where you have nulls. Theta is 0 and theta is 270. Minimum radiation where it is occurring, this theta 0, 90, 180, 270. So minimum radiation is occurring at 90 and 270. In Indified array, half power points occur at, take an Indified array, the half power points occur at this is an Indified array, the radiation pattern. In Indified array, half power beam width occurs at this 3 dB down, this 3 dB down. They occur at 60 and 120. Radiation pattern of Indified array by default it is unidirectional pattern. In Indified couplet, radiation pattern is Indified generally the radiation is unidirectional, but in a couplet, that means two arrays spaced lambda by 4 fed by 90 degrees. Then in this case, the radiation will become bidirectional. Indified array generally the radiation is unidirectional, but under these cases it will become bidirectional. In Indified couplet, the radiators are separated by lambda by 4. In Indified couplet, the radiators have a phase shift of. In Indified couplet, the radiators have the phase shift of. They separate by distance lambda by 4, phase shift is 90 degrees. Points of dash are same in Indified array and broadside array. Points of dash are same in Indified array and broadside array. Points of dash are same in Indified array and broadside array. In Indified array or broadside array, this is Indified array. This is Indified array. In Indified array, the points of dash are same in Indified array and broadside array. This what I have drawn here is broadside array with radiation is max at 90 and 270. The points of dash are same in EFA and BSA. If you take half power points, this will be at 60 and minus 60. Clear? So, if you draw the Indified array, Indified also looks like this. It looks like this, Indified array. Now if you see, again here 3 dB down, that means what? The points of dash are same in Indified array and broadside array. The points of half power point, the points of half power are same in Indified array and Broadside array. 20th question, option C is the answer. I repeat it, points of dash are same in Indified array and Broadside array. Those are half power points which are same. Clear? Next we'll continue our discussion on parasitic arrays. What is the difference between broadside array, Indified array and collinear arrays? In broadside array and Indified array, array axis and individual antenna axis will be different. For example, this is the individual antenna axis and this is the array axis. They both are different. Whereas for collinear arrays, the array axis and the individual antenna axis both will be same. This is the best way to define collinear arrays and differentiate between collinear arrays and broadside arrays and Indified arrays. Okay. So what is the question? Collinear arrays. Collinear arrays. Collinear arrays will result in maximum gain and the spacing between the elements is dash to dash. How much should be the spacing is asking. Everyone try to answer how much should be the spacing so that this array will result in maximum gain. That's the question. Yes. Anyone? Can anyone answer this? Anyone, dear? How much should be the spacing? The collinear array. So that you get maximum gain. So that you get maximum gain. Very important question, dear, because almost like we need to memorize this kind of thing. And the memory based questions where you need to memorize the concept, they are very important actually in one point, because you cannot prove anything there. You must remember, that's it. So at one point, these kind of questions are also very, very important. So I had given you the difference between broadside array, Indified array and collinear arrays. Geometrically they are different. Okay. Geometrically they are different. And the spacing between the elements in a collinear array must be between 0.3 lambda to 0.5 lambda in order to have the maximum gain. For question number 1, option B is the answer. Question number 1, option B is the answer. Next question. A collinear array with two elements result in a gain of dash dB. A collinear array with two elements result in the gain of dash dB. Result in a gain of dash dB. A collinear array with the two elements, again memory based questions, very important. Collinear array with the two elements results in a dB of 1.9 dB. Results in 1.9 dB. Collinear array with four elements results in gain of dash dB. Again memory based questions. I'll tell you a simple logic here. Listen here. If you take a collinear array with the two elements, the maximum gain is 1.9 dB. Three elements is 3.2 dB. Four elements is 4.3 dB. With four elements, it is 4.3 dB. Clear? So that's the best way to remember, easiest way to remember also. Memory based questions, these are also very, very important. Next question. A phasing stub is used in collinear arrays to make the current dash. Why do you use a phasing stub? What is the phasing stub here? This is first element, element number 1. Collinear array. This is element number 2. This collinear array. Element number 3. This element number 4. Each are of length lambda by 2. Each are of length lambda by 2. When you feed a current, you know current after every lambda by 2, the current will reverse its phase. So what we do is we try to keep a phasing stub here. Whose total length is lambda by 2. This current will be here. The negative current will be, the negative cycle will go here. Then continuation positive. Now this and this are in phase. In the phasing stub, the current is going downward here. Here it is upward. They cancel out. Therefore, this fellow will not result in any radiation. The phasing stub will not result in any radiation. It is only just to make the phase correction. Now, the same thing is valid for the next phasing stub. Negative cycle will go here and the positive cycle will come here. So, because of this phasing stub, what is happening is the current is going in phase. So, a phasing stub is used in collinear arrays to make current in phase. In phase. Option A is the answer. Please tell me, is that clear? Is that clear, everyone? Good. In parasitic arrays, element to which power is supplied is called as, what is a parasitic element or what is a parasitic array here? A parasitic array contains a driven element to which the power is directly fed or from which the power is directly taken. This element is called a driven element. And all the others are not physically connected, parasitically connected. The one which is 5% less in height, these are directors. One is 5% greater in height when compared to driven element. This is reflector. Now what is asking in parasitic array? Element to which power is supplied is called as the parasitic array. The element to which the power is supplied or from which the power is taken out is called as driven element. Driven element. Option B is the answer. Driven element. Option B is the answer. In a parasitic array, element which is maintained a height 5% less than the driven element is called as just now I told you, this is a driven element. Then the element which is having a height 5% less than the driven element, these are called as directors. Height will be 5% less than driven element, and the element for which height is 5% more than the driven element is called reflector. Now see the question. In parasitic array, element which is maintained a height 5% less than the driven element is called as director. Is called as director. The following is an example of parasitic arrays. The following is an example for parasitic arrays. Which antenna is example for parasitic arrays? Dipole antenna, monopole antenna, Yagi-Uda and all. Dipole and monopole are resonant antennas. They are not an example for parasitic, but Yagi-Uda antenna, which contains a driven element as folded dipole antenna mostly, and a set of directors which are having 5% height less than the driven element. And one or more reflector which is having a height 5% more than the driven element. There will be a horizontal rod to hold this. There will be clamps to hold this. There will be a vertical rod on which it is installed. The old-fashioned, the antenna, which is used for television reception. Even today, if you go village side, you can see these kind of antennas still in place. This is nothing but a Yagi-Uda antenna, which is only for this driven element. The cable is directly connected. All other are parasitically excited. Therefore, this kind of array is called as a parasitic array. So, Yagi-Uda antenna, which is also called as super gain antenna or super directive antenna, is the best example for a parasitic array. Clear? Yagi-Uda antenna exhibit what? High FBR, front to back ratio, beam area, antenna temperature, all. First thing, antenna temperature. If you talk about antenna temperature is not an internal parameter of an antenna. Antenna temperature depends on the temperature of the surrounding. So, this is outruled. Yagi-Uda antenna is also called as a super gain antenna or super directive antenna. It can transmit or receive very effectively in a given direction. It's a super directive antenna. It contains a driven element, series of directors, and a reflector. Now in this diagram I have shown you 5 elements. In this way you can have maximum of 40 elements, and these directors will help the antenna to radiate more in a given direction. It's called a super gain antenna. It also gives you unbelievable 40 dB gain. 40 dB is so much. For every 3 dB the power will get doubled. 40 dB you can just imagine. 40 dB is a very big number. The signal strength will be improved by 10,000 times. Unbelievable, am I right? Total number of elements that a Yagi-Uda antenna can have maximum of 40 elements. Therefore, this is called a super gain antenna or super directive antenna. It is giving you more gain or more directivity. You know, directivity is 4 pi by omega A. If it is having high directivity, it must have low beam area. So this is wrong. So what is left out? FBR. FBR stands for front to back ratio. That means if you draw a radiation pattern of antenna, this is the main lobe, these are side lobes, these are minor lobes, and this is back lobe. This is main lobe, these are side lobes, these are minor lobes, and this is back lobe. The ratio of power associated with the main lobe or front lobe to that of the back lobe is called front to back ratio. And this front to back ratio, FBR, is practically equal to directivity. We prefer high FBR. So Yagi-Uda antenna exhibit what? High FBR or directivity. Therefore, question number 8. Option A is the answer. Is that clear? Operating frequency of parasitic arrays. Now I explained you about parasitic arrays. Yagi-Uda antenna is an example of parasitic array. Then what is the operating frequency that is suitable for parasitic arrays? That is what is asking. Parasitic arrays can be operated between which frequencies? Parasitic arrays can be operated between which frequencies? Parasitic arrays can be operated between which frequencies? Parasitic arrays are most suited frequencies between 100 MHz and 1000 MHz. Option A is the answer. Question number 9. Option A is the answer. The problem of using phasing stubs. The problem of using phasing stubs can be avoided by using which kind of arrays? Because in collinear arrays, as I told you, in collinear arrays, in order to correct the phase of the current, we use phasing stubs. In the just before question, I explained you about phasing stubs, how phasing stubs will nullify these negative currents or negative cycle currents. The problem of using these phasing stubs can be avoided by using what kind of arrays? By parasitically exciting him. Instead of physically exciting, parasitically exciting. That is, by using parasitic arrays. Example, Yagi-Uda antenna. So question number 10. Option C is the answer. an array of 2-point sources, an array of 2-point sources fed with equal current or fed with current of equal amplitude. Let me say in that way. Fed with current of equal amplitude and phase results in dash pattern. Whenever you feed two elements with equal amplitude and same phase, it results in broadside array pattern where radiation will be perpendicular to the axis of the array. This is the axis of the array axis. Then the radiation will be perpendicular to the axis of the array. Figure of 8 pattern. Figure of 8 pattern. Therefore, whenever you feed two elements with the current of equal amplitude and same phase, it results in broadside array. Question number 1. Option B is the answer. An array of 2-point sources fed with current of equal amplitude, again equal amplitude, and progressive phase shift. Remember dear, when you feed current with equal amplitude and same phase, it results in broadside array where the radiation is perpendicular to the axis of the array. Figure of 8 pattern. When you feed current of equal amplitude and progressive phase shift, that results in Indified array. It will fire at the end of the array. This is a 2-element array. This array axis will fire at the end of the array like this. And it will be generally unidirectional. And these are generally bidirectional. Clear? So what is given? An array of 2-point sources fed with current of equal amplitude and progressive phase shift results in Indified array. Now equal phase shift is very simple, but what do you mean by progressive phase shift? Progressive phase shift. I'll explain, don't worry. See, if I am considering two elements separated by distance lambda by 2, progressive phase shift means if you take a wave, take one cycle of a wave, the distance covered by the wave is lambda. This is 0. This is lambda by 2. This is 3 lambda by 4. This is lambda by 4. If you take the phase shift, here the phase shift is 0. Pi by 2. Here pi. Here 3 pi by 2. Here 2 pi. Now, what do you mean by progressive phase shift is? Progressive phase shift means if the phase difference or the phase shift is proportional to the distance, then we call it as progressive phase shift. For example, if the distance between the two elements is lambda by 2, then the phase shift, if it is maintained, is pi, then it is called progressive phase shift. If the distance between the elements is lambda by 4 and the phase shift maintained is pi by 2, it is called progressive phase shift. If the distance between the elements is 3 lambda by 4 and the phase shift maintained is 3 pi by 2, these cases are called as progressive phase shift. Clear? And now if you maintain progressive phase shift, equal amplitude and progressive phase shift, then it results in Indified array. Donut pattern. Donut pattern. If you take the 3D image of this, it looks like a donut. Donut which is cut into half. This is also, it also looks like donut, but I want to differentiate. Therefore, this is called figure of 8 pattern. This is called figure of 8 pattern. This is called donut pattern. For our clarity. An array of 2-point sources fed with current of equal amplitude. Amplitude is equal, E1 is equal to Et is equal to E0, and phase difference alpha is equal to 0. No phase difference means same phase. Equal amplitude and same phase. Distance is lambda by 2. Equal amplitude, same phase, distance lambda by 2. It is a case of broadside array. Broadside array means what is the pattern here? Anyone? Broadside array means it results in figure of 8 pattern. For option A is the answer. Now, but you may ask me, sir, what is the proof for this? Let me tell you. The resultant electric field, mod of Et is E0 into cos psi by 2. If you want to take the normalized pattern for drawing the radiation pattern, Et norm is cos of psi by 2. The psi is phase difference given by beta d cos theta plus alpha. Therefore, this is cos of beta d cos theta plus alpha by 2. Given in the question, alpha is 0, phase difference is 0, distance is lambda by 2, and of course you know phase shift constant beta is 2 pi by lambda. Substituting this cos of 2 pi by lambda into lambda by 2, cos theta plus 0 by 2. This cos of this 2 get cancelled, lambda get cancelled. Cos of pi cos theta by 2. That's your normalized pattern here. So try to draw the pattern. Try to draw the pattern. Everyone try out. Now I already told you shortcut. But now I am telling you procedure. Shortcut is what? Equal amplitude, same phase, distance lambda by 2. Broadside array, figure of 8 pattern. Option A answer, direct. But now procedure. Theta is 0 degrees, theta 90, theta 180, theta 270. Theta is 0, cos 0, 1, cos of 90, 0. No radiation here. No radiation here. Next. Theta is 90, cos 90 is 0, cos 0, 1, maximum radiation. 180, cos of 180, minus 1, cos of minus 90, cos 90, 0, no radiation. Next. Cos of 270. What is cos of 270? Cos of 360 minus 90. Cos of minus 90. Cos 90. 0. 0. Okay. So, cos of 270. This is 0. Cos 0, 1. Maximum radiation. Cos of 270, 360 minus 90, cos of minus 90, cos 90, 0. Fine. So this is 0. And once you substitute, it's cos of 270. This is getting 0, cos 0. This is one maximum radiation. Now this is what? Figure of 8 pattern. Figure of 8 pattern. After doing all the analysis, you got figure of 8 pattern. In shortcut also I told you the same thing. Is that clear, everyone? Next one. An array of 2 point sources. An array of 2 point sources fed with current of equal amplitude and phase difference alpha 180 degrees, spaced d lambda by 2. When distance is lambda by 2, phase shift is 180, means it is progressive phase shift. Equal amplitude and progressive phase shift. Equal amplitude, progressive phase shift. It's a case of Indified array. Therefore, donut pattern, option B is the answer. This is shortcut. If you have this knowledge, directly you can write. Or you can go for procedure. What is procedure? Mod of Et is E naught into cos of psi by 2. Mod of Et normalized is cos of psi by 2. Psi is beta d cos theta plus alpha. This is cos of beta d cos theta plus alpha by 2. Beta is 2 pi by lambda. Given distance is lambda by 2. Alpha is 180 or pi. Substituting, psi is equal to 2 pi by lambda into lambda by 2 into cos theta plus pi. Psi is pi cos theta plus pi. I want psi by 2. It's cos of pi by 2 cos theta plus pi by 2. Now trying to draw the pattern. Try and draw the pattern. Theta is 0 degrees. Theta 90. Theta 180. Theta 270. Now, theta is 0. Cos 0, 1. Mod of Et normalized. Cos 0, 1. Cos pi by 2 plus cos pi by 2. Cos pi, cos 180 minus 1. But it is in mod. For you take the maximum amplitude. 90. Cos 90 0. 0 plus 90. 90. Cos 90 0. No radiation. 180. Cos 180 minus 1. Minus pi by 2 plus pi by 2. 0. Cos 0 1. Maximum radiation. Maximum radiation. What is this? Donut pattern. That's what I told you. Next, cos of 270. 0. 0 plus pi by 2, cos 90, 0. 0. This is donut pattern. Therefore, you can say option B is the answer. This after doing all this derivation you can tell, or if you are having knowledge you can directly tell. Next. An array of 2 point sources fed with current of equal amplitude and phase difference of alpha is 90 degrees, spaced at a distance of lambda by 4, results in which pattern? Let me write. Array of 2 point sources fed with current of equal amplitude, phase difference 90, distance lambda by 4. In this case, procedure will be useful. So let me do the procedure. Mod of Et is E naught into cos of psi by 2. Et normalized is cos of psi by 2. Psi is phase difference given by beta d cos theta plus alpha. Psi by 2. Beta d cos theta plus alpha by 2. Beta is 2 pi by lambda. Distance is lambda by 4. Alpha given is pi by 2, I think. How much? Alpha 90, pi by 2. Substituting, this is 2 pi by lambda into lambda by 4 cos theta plus pi by 2 by 2. Lambda get cancelled. Pi by 2 cos theta plus pi by 2 by 2. Pi by 4 cos theta plus pi by 4. Et normalized is cos of pi by 4 cos theta plus pi by 4. Solve it. Theta is 0 degrees, theta 90, theta 180, theta 270. Theta is 0, cos 0 1, pi by 4 plus pi by 4, pi by 2, cos 90 is 0, no radiation. No radiation. Next 90, cos 90, 0, 0 plus pi by 4, pi by 4, cos pi by 4, 1 by root 2, 0.707. Next. Cos 180 minus 1 minus pi by 4 plus pi by 4 1, that is minus pi by 4 plus pi by 4 cos 0. Cos 0 is 1, maximum radiation. Next 270, cos 270 is 0, cos of pi by 4 1 by root 2, 0.707. Now if you try to add them, 0, 1 by root 2, maximum, 1 by root 2, here maximum. You get this kind of a pattern, heart shaped pattern. So what's the answer here? Option C is the answer. Therefore option C is the answer. Is that clear? That's why knowing procedure is very important. We can solve any concept. If you know the procedure, you can very easily solve any concept. Next question. An array of 2 point sources fed with current of equal amplitude and phase difference of alpha is minus 90. Space distance lambda by 4 results in dash pattern. Let me write down what is given. Two point sources fed with current of equal amplitude, phase difference minus 90 degrees, spaced at distance lambda by 4, results in dash pattern. In this case again, the procedure will be useful. Mod of Et is E naught into cos of psi by 2. Where psi is beta d cos theta plus alpha. Mod of Et normalized is cos of psi by 2. Cos of beta d cos theta plus alpha by 2. Beta 2 pi by lambda. Distance given lambda by 4. Alpha given how much? Minus pi by 2, I think. Minus 90, minus pi by 2. Minus pi by 2. Substituting, psi is 2 pi by lambda into lambda by 4 cos theta minus pi by 2. This is pi by 2 cos theta minus pi by 2. Beta d cos theta plus alpha by 2 is there. Cos of pi by 4 cos theta minus pi by 4. Now do it. Everyone do it and tell me the answer. Theta 0 degree, theta 90, theta 180, theta 270. What's the answer here? Theta is 0, cos 0 is 1, pi by 4 minus pi by 4, 0, cos 0, 1, maximum radiation. Maximum radiation. Next, theta is 90, cos 90, 0, cos of minus pi by 4, cos pi by 4, 1 by root 2. Cos 180 minus 1 minus pi by 4 minus pi by 4 minus pi by 2. Cos of minus pi by 2 cos pi by 2 cos 90 0 0. Cos of 270 0 0 minus pi by 4 cos of minus pi by 4 cos pi by 4 1 by root 2 0.707. You draw the pattern. This is 1 here. 1 by root 2, 0. You will get a pattern something like this. Option D is the answer. If option D is the answer. Is it clear? One second here. Okay. Okay. Next. An array of 2 point sources an array of 2 point sources fed with current of equal amplitude, same phase, alpha is 0, but distance is lambda. Alpha 0, but distance is not lambda by 2. If distance is lambda by 2, figure of 8 pattern, but distance is lambda. Now in this case also, our analysis will be useful. Let me do the analysis. Mod of Et is E naught into cos of psi by 2. Psi is beta d cos theta plus alpha. E naught into cos of beta d cos theta plus alpha by 2. Beta is 2 pi by lambda. Distance d is lambda. Given alpha is 0. Substituting psi is 2 pi by lambda into lambda cos theta plus 0. Psi is 2 pi cos theta. Psi by 2 is pi cos theta. E is equal to E naught into cos of pi cos theta. Et normalized is cos of pi cos theta. Take the values. Theta is 0 degrees, theta 90, theta 180, theta 270. Do it. Do it here. Theta is 0. Cos 0, 1. Cos 180 minus 1. Magnitude, it is in mod, so you will take maximum. Next. Theta is 90. Cos 90 is 0. Cos 0, 1 maximum. Theta is 180. Cos 180 minus 1. Cos of minus 180. Cos 180 minus 1. It is in mod, maximum. Cos of 270, 0. Cos 0, 1. Maximum. You get flower shape pattern. Option C is the answer. Option C is the answer. Got it here? Next. F and BW, beam width between first nulls of a broadside array of length L is equal to lambda. Now for this you should know the formula for F and BW for a broadside array. F and BW for a broadside array is given by 2 by L by lambda radian. L is lambda given, they cancel out. The answer is 2 radian. Converting into degrees, 1 radian is 57.3 degrees. But the answer is 114.6 degrees. Therefore, option B is the answer. Question number 8, option B is the answer. Half power beam width of a broadside array with array length L is equal to lambda is, you must know half power beamwidth formula for broadside array. For a broadside array, half power beamwidth is given by 1 by L by lambda radian. L is lambda, so answer is 1 radian. In terms of degrees, 57.3 degrees. Option A is the answer. Is that clear? Is that clear? F and BW, again, F and BW of a broadside array with length L is equal to 10 lambda is, what is asking? F and BW, which array? Broadside array is 2 by L by lambda radian, given L is 10 lambda. L is 10 lambda, that is 2 by 10 radian. L is 10 lambda, 2 by 10 radian. Therefore, F and BW is asking 2 radian, it is 0.2 radian. 114.6 by 10, 11.46 radian. Option B is the answer. Option B is the answer. Next. Half power beamwidth of a broadside array. For a broadside array, half power beamwidth formula 1 by L by lambda radian, given L is equal to 10 lambda. L is 10 lambda, this is 0.1 radian, 57.3 by 10, 5.73 degrees. Option A is the answer. Option A is the answer. Clear? Fine. Fine, what we do is, we'll try to end up here. We'll try to end up here. These problems we'll do in the evening session, 9 p.m. session, okay? Unacademy offers 2 paid platforms. One is Plus subscription, other is Iconic subscription. In Plus subscription, you got to have the face time of legendary faculties in form of live classes, weekly test, structured courses, unlimited access, rank improvement batches and crash courses. And remember, in Plus itself we have both rank improvement batches as well as crash courses. Unlike other platforms, on other platforms you can see they'll charge separately for rank improvement batches as well as crash courses, but we don't do that. In Plus itself we have both. And also, if you take Iconic subscription, you'll have all these features of Plus subscription. Along with that, you have a personal coach for one-on-one guidance, dedicated doubt clearing educators to clear your doubts, customized study planner, study booster sessions, personalized test analysis and preparatory study material. All this in Iconic subscription. Whether going for Plus subscription or Iconic subscription, you can go for a no-cost EMI. That means total cost will be divided by number of months without any extra charge. And moreover, if you are using our team code KNR10, remember, not the individual code, but team code KNR10, you'll not only get 10% off, but you'll get uniquely all the team support of the Gate Conqueror channel. All the faculty support you'll get only by using our team code KNR10. Please remember. And by Iconic subscription, you get 1:1 live mentoring, increasing your chance of getting a top rank. This is Unacademy Accelerate. No breaks in your preparation. Free 6 month extension on subscriptions of 1 year and above. The limited period offered here. You can use our team code KNR10. As I told you, you'll not only get extra 10% off, it's a golden opportunity. 6 months extra subscription we are giving away. And if you are having any doubts in your preparation journey, subscription, latest offers, you can get in touch with our counselor. You can call on this number. Unacademy has introduced a feature called Ask a Doubt feature, through which you can ask unlimited number of doubts. And this Ask a Doubt, previously it was available on app, now it is available on website also. At a time you can ask 3 doubts and you can get the solution in your preferred language. And also it is very easy to ask your doubts. Click, crop and submit. The super combo offer going on. With every 2 year subscription we are giving away 1 year subscription free for campus placement and IT jobs. With 1 year subscription we are giving away 6 month subscription for campus placement and IT jobs. This is the rank predictor for GATE 2022 DIA. Very easy. Just log in, go to GATE landing page, then click on the rank predictor banner, select your stream, select your session, paste URL, your rank will be appearing. And these are the special class features DIA, which includes interactive live classes, polls for the learners, raise hand option. You never miss a class when the notification is on, and you can download the lecture notes once the class is done. You can access anytime and anywhere. We are introducing community DIA, through which you never miss any updates from your favorite educator. First thing. Second, you can download notes and practice material, and also you can share the feedback with your favorite educators directly via polls. As you know, every week we start new batches. These are the new batches. We started in the last week. Resilience for GATE 2023 for electrical explained bilingual. Resilience GATE 2023 EC explained bilingual. Ascent GATE 2024 EC explained bilingual. Ascent GATE 2024 electrical explained bilingual. Evolve GATE 2023 electrical explained bilingual. Evolve GATE 2023 EC explained bilingual. These are the new batches. For all the batches, you can use our team code KNR10. You'll not only get extra 10% off, but also you'll get complete team support. Thank you all dear. Thank you all for joining. Let us meet in the 9 PM session. Thank you all.